session 1, Podman Introduction. Agenda of the session is use case for Podman. What is Podman? Containers versus virtual machine. Advantages, architectures, and images and containers. So what is Podman? Podman is a daemonless container engine. When I say daemonless, that is the difference between Docker and Podman. Docker run as a daemon process, which means which is always in on non-terminating mode running the backend, and which takes the calls from you through the command line CLI, which is Docker itself. Podman is not running permanently. It takes the request and then accordingly it will act on the command you send to it. So that's the main difference between Docker and Podman. Podman is a daemonless, whereas a Docker is a demonized process. It is a replacement or alternative to Docker for managing and running containers on your Linux system. Containers can either be run as root or in a rootless mode, depending on whether you are running them as root or in a rootless mode. What are the use cases for developers? Build once, run anywhere. It is a clean, safe, hygienic, and portable runtime environment for your application. You should not worry about dependencies, packages, and other pain points during subsequent deployments because the container image include everything. That include the library files, that include the uh, dependencies, that include the executables, that include the configuration files. Everything is included inside the container. So you can simply run it anywhere you want. During each app, run your in each app in its own isolated container, so you can run various versions of libraries and other dependencies for each app without worrying. What does it mean? What this statement is actually pointing to? It is pointing to an example that if I want to try my application on MySQL 5.7, MySQL 8, and MySQL 4, can I have four versions of MySQL running on the same system without worry? Answer is absolutely yes. Because you can have multiple environments, you can create multiple environments for your application and test them. Or maybe just, I'm talking about one database. You can create such environment for any other use case also. For example, specific PHP version or libraries or anything else. So it is not just about database. So you can have different versions or different settings for each of the environment, and you can create such isolated environment for application with containers so easily without worrying. Automate your testing, integration, packaging, anything you can script, you can create a container for that. Reduce or eliminate concerns with about compatibility on different platforms, either your own or your customers. Configure once, run anything. Make the entire life cycle more efficient, consistent, and repeatable. Increase the quality of code produced by developers. Eliminate inconsistencies between development, test, production, and customer environments. These are use cases for DevOps. It supports segregation of duties. It significantly improves the speed and reliability of continuous deployment and continuous integration systems. You will understand that during our Kubernetes topic because we have a comprehensive set of examples and training on the subject. How can we have this speed and reliability? What is the tool or what will lead to this speed and reliability of CD and CI? Because the containers are so lightweight, they address significant performance, cost, deployment, and portability related issues normally which are associated with the virtual machines. Yes, you will see the real examples of this lightweight concept, performance related issues, deployment and portability, because we will be using them in our Kubernetes, and which will make the difference, lot of difference in addressing these issues. So these are the use cases for DevOps. Containers. What is a container? Containers are represented by these shipping containers. Why? I don't know. Many people never try to understand the reason, but I have a reason for it. These containers, shipping containers are used because across the globe, you see any shipping container, you will find the same standards. Like the corner will be the same, the bottom will be the same, the roof will be the same. Even the lining, you see that this is not straight sheet of iron. It is you see the dents are there. So the corners or top or bottom or door or front, everything is governed by standards. In containers also, there are many aspects of containers. Every aspect of container is governed by standards. Therefore, and also the isolation, because whatever you put inside this container, that will remain isolated from the rest of the world. So standards and isolation are the two regions, good regions, to use this as a symbol for container representation. So it is operating system level virtualization method for running multiple isolated Linux systems or containers on a single host. You know that when we talk about virtual machine, we are talking about a villa or a house. So that you get complete isolation, it is fully owned property. So when you have a hypervisor based virtualization on your infrastructure, you install operating system. On the top of that, you install hypervisor, and then you create your guest machines, guest operating system, binaries, libraries, and application. Take your own example right now, what we have done. On our Windows machine or Mac machine, we install the hypervisor. In our case, the hypervisor is Oracle VirtualBox. Actually, this Oracle VirtualBox is type 2 hypervisor. What is type 1 hypervisor? Type 1 hypervisor is the one which is directly installed on the hardware, like RHEVM, Red Hat Enterprise Virtualization Manager. It is a lightweight OS plus full-fledged hypervisor. So only the kernel is included. Apart from kernel, though no application, nothing else is there. Only the hypervisor is there, which is controlling the hardware directly. So when we talk about type 1, they are directly installed on the top of the hardware to create virtual machines. Type 2 is which is installed on the guest operating system. So on the host operating system. In our case, our Windows machine or our Mac machine is the operating system on the top of which we installed Oracle VirtualBox. That's why Oracle VirtualBox is type 2 hypervisor. So once the hypervisor is installed, whether type 1 or type 2, we create the guest VMs. So in our case, Linux Server 1 is our guest machine which is created. Similarly, we are going to create tester 1 also. You can have Windows machine also. You can create any guest machine for that region. Whereas when we talk about containers, containers are like apartments in a multi-story apartment building. Look at these apartments. So this is one container, this is another container. They still give you isolation, but they are somehow connected or rely on the same building. They have dependency on the building. They are closely knit, but they share the resources. So the containers comparatively give you less isolation, less security, or less this thing, but they still offer you isolation. So how we create them? We install operating system, we install container engine, daemon based or daemon less, and then we run our application inside the containers. This is the picture from a user perspective. We are not just users, we are little more than that, because we want to containerize our application, we want to run it, and more importantly, we want to visualize it, how it is actually working inside the kernel. So we need to look at from that perspective of also from the kernel perspective, how these containers are created. So first let's look at the big differences. Containers versus virtual machines. Security wise, virtual machines are more isolated, they are comparatively less isolated. Size wise, they are more huge or bigger in size, their size in gigabytes. Containers are in megabytes. Provisioning, virtual machine take few minutes, but containers a few seconds. It is so lightweight. Operating system wise, virtual machine gives you more flexibility, containers are less flexible. That is the difference. Change the way we think. Image registries, container images, containers and OCI or containers. We need to change our mindset, change our thinking. What do you need to create a container? You need a way to pull the images from from a registry where the images are kept like ISOs. So you need to pull these images from the registry. Ability to store these images on the disk. You probably have to create a storage or image registry on your local machine also to pull these images from the registry to your local machine. And you need to a runtime to use application based on this image, that is called a runtime, so that we can actually see the application running. Simply ISO on the DVD will be of no use. Whatever application you have on your DVD, you need to run that, you need to start that as an application. Ability to set up networking between the containers, between the host machines, and maybe some kind of monitoring. We need to look at that aspect also. What are the Podman advantages? It supports multiple image formats. Support for multiple means to securely download images. Container image management, managing image layers, overlay file systems, etc. Full management of container lifecycle, meaning creating images, launching containers based on images, creating storage, attaching storage to containers, linking containers. Supports for pod to manage group of containers together, which is actually a main region for using this Podman for Kubernetes. So because in Podman, the term pod we use heavily. In fact, in Kubernetes, this is the first building block we create. First step we create is pod. So pod technically can be defined as a group of containers, maybe one container or more than one containers together, and a resource isolation of containers. Kernel and containers, this is what I was talking about. The difference, the looking at the containers from the kernel perspective. From the kernel perspective, there's nothing called container. Let me be very clear, and I'm absolutely sure about it. Because I'm a developer, I'm a programmer, and I talk about system programming, writing, creating modules for kernel also. I know how internally Linux works. Linux kernel can be divided into two spaces. One is the kernel space, let's call it as KS, and second is user space, let's call it as user space. User space cannot interfere, cannot mess with the kernel space. It can only make system calls for resources, and kernel can allocate that to the user space. So kernel space is always protected, and only interaction with the kernel is by making the calls like fork system call, exec system call, exit system call, kill system call, open, close system. These are all the calls which we make to the kernel to manage our processes and to run applications on Linux. There's no confusion on this. Container does not fit into any of these things because this is how the regular processes are created. Because what we do, we issue a command from the shell. When you execute any command, it will make the appropriate system call to the kernel, and it will create regular processes in the user space. I'm trying to make it clear that where the containers from this definition, where are the containers? Containers are not existing in this case. So if I have to define it from the kernel perspective, how will I define it? Creating containerized Linux processes. What are containers anyway from this point of view? There is no kernel definition of what a container is, because in kernel we have only processes. That is the main problem. So if I have to define it, what is the closest definition? I have the closest definition as when I use the system call called clone. When I make the system call clone to the kernel, it will create a clone of these kernel processes. That is all the data structures. So it will create a clone of these data processes, data structures, virtualized data structures by using this clone system call. So this clone system call will create namespaces for kernel resources like mount, UTC, IPC, PID, network, user, everything. Essentially, it is virtualized data structures. Now, this is which will clarify the difference between Podman and Docker also. Whether it is Podman or Docker or anything else, they have to make this call, system call, when the containerized processes are created. Only difference now you understand, Docker is running at a daemonized process, backend process, which is all can interact with making these calls to create these containerized processes. Podman is a standalone application which you can execute anytime to send to make these system call. Ultimately, managing these containerized processing is making the system calls, appropriate system calls for your containerized applications. Whether you send the calls through container or through Podman, and if you say RAM, is it possible to develop your own? Absolutely yes. Because if you ask me, give me 4 5 days, probably a week time, and I'll come out with a bare minimum container management system by at least creating those system calls, making those system calls. Because ultimately what interaction, how these processes interact, that comes altogether a different topic. How the networking works, how the storage shared, that is altogether different, because that comes under IPC, inter-process communication, and there are multiple ways for inter-process communication, like shared memory, semaphores. So there are many ways for sharing the for interacting for the interaction between the processes. So interaction, storage, and everything is handled by different system calls, and we have appropriate calls for that. We can create our own system calls as well. So this is what the container is from the Linux perspective. Podman architecture. The pod concept was introduced by Kubernetes. Podman pods are similar to the Kubernetes definition. So when we create a pod, it will create a virtualized data structure, what I was talking about in the previous slide. IPC, net, PID, namespaces, control groups. So this container monitoring, container management, so we have infra container, container A, which is a run C, container B, which is run C. These are containers which you create using Podman. Every Podman pod includes an infra container. This container does nothing but goes to sleep. Now, see, this is what you can compare it with the daemon of Docker. What is the purpose of this infra container? The purpose is to hold the namespace associated with the pod and allow Podman to contact other containers to the pod, and hence that is the purpose. Can we compare with any other process of Linux with the same? My answer is yes. There is a process called min-getty. The min-getty process has a similar job, which is responsible for logging in, logging out with the system, which wakes up when you log out and which goes to sleep after you log in, and it remains sleeping mode. This allows you to start and stop containers within the pod, and pod will stay running, whereas if the primary container controls the pod, this would not be possible. The default infra container is based on the K8 GCR pods image, unless you explicitly say otherwise. All pods will have container based on the default image. That is the architecture how Podman run the containers. Images and the containers, let's look at that part also. By definition, images are read-only templates which are used to create containers built by you or by anybody else, stored in redhatquire.io or Oracle Container Registry.oracle.com or locally on or Docker Hub, wherever you want to keep. There are multiple locations where you can store. Every image starts with a base image. Well, not always, because you can start an image from a scratch also. So by default, it is read layer, read layer, read layer, and unioning of these layers will make one image. Therefore, the simplest definition of image is unioned read-only file system, which will include your application, dependencies, libraries, binaries, and configuration files. Whereas containers are application platform, contains everything needed to run your application based on one or more images. So we have image layers you can see, but we add one more layer here, read write layer. And the unioning of these layers, read only layer for the images and the read write layer for the container, will make a container. So therefore, it is unioned read write file system. So Podman containers are launched from the images. When particular Podman container runs, it runs a read-write layer on the top of the image. Those who are object-oriented programming, those who have the understanding of object-oriented programming, think of Podman as Podman image as a class and container as an instance of the class. So image layer, read layer, write, read, write layer make the container. So this is the container. These are images. So here also kernel image, add a writable layer will make it container. LXC, AutoFS, BTRFS, BusyBox, writable layer will make it container. Debian, Emacs, Apache, add writable layer will make it container. Till then we have the image. So we have the image at the back end, behind the screen, and we add a writable layer, and that is the container. Volume, that is storage. Volumes for persistent data generated and used by containers, which you want to store outside the container. Easier to backup and migrate than bind mounts. What is bind mounts? Say you have a container running. Obviously, if take an example, if you are running a database, you want to store the data on the disk. So you want to associate external storage. You want to attach external storage with this container. How can we have that? There are three options. One, you use bind mount. Bind mount means you associate a physical path from your file system to this container. So all that data from the container or generated by container will go to that path. Whereas if you say volume, that can be used to store the data. In that case, you are creating a NFS server or you are using simply another driver. So use any driver which is supported to create the storage outside the container, but fully managed by container. So the whether it is NFS driver you are using or you are using the remote storage driver, with appropriate storage driver, you can use external storage which will be used by your container management system. When you are using volume, that will be easier to backup. Why? Because it is if it is NFS server, you literally don't have to do anything. You can use it wherever you want, or probably you can have same storage mounted as a read write on one container and read only on another container. Whereas the bind mount will tie or make it absolute fix with one specific machine, because you cannot migrate it. Or if you are doing it, you have to create the same path, because it's specific. In that case also one more picture will come, that what operating system and what is the character set you are using. There are multiple concerns will come into picture. Volumes work on both Linux and Windows containers. Volumes can be more safely shared among multiple containers. As I said, we can have read only for one container, read write for other. Volume driver let you store volume on remote host, as an example NFS I was talking about, or cloud providers to encrypt the containers or to add other functionality. Volumes can have their content pre-populated by a container. That's also interesting use case. This is the figure I drawn in the previous website, previous slide. Container, physical path of the file system, bind it, We call it as bind mounts. Whereas volume fully managed by the container. So by means of appropriate driver, that becomes the Docker area or the container area. Another way is temp fs mount. So this is the Podman volume concept. That's all for this session. Thank you very much, team.